Alright, here is your homework number 5 helpful hint video to kind of help you out with these two problems that I want you guys to do. But these guys are real important problems because they're going to set the stage for future problems as well. So this one is the idea of being able to prove you have a subring. So in this particular problem, let phi be a mapping from R to S be a homomorphism from ring R to ring S. Another way I could have stated that was let phi be phi be a mapping from R to S be a ring homomorphism. That kind of screams volumes that phi is the homomorphism and R and S are rings. And let K be equal to the elements little r from big R such that when I take phi of R, it's equal to 0s. We're going to prove that K, which is that, mentioned it before, this is the kernel of the mapping phi, is a subring of R. So the key to it is, first, you've got to actually pay attention to the set that you're talking about. We were given R and S are rings, and K are the elements. This first part is where you come from. So to be in K, you had to come from R. Little r is element of big R, and this is the property you have. It's the same element. Phi of R is equal to 0 in S. Now, to prove you have a subring, we're going to quote the famous Theorem 3.6 that you have memorized. Theorem 3.6 says you got to prove three things. One, you got to prove it is non-empty. Two, you got to prove closed under subtraction. And number three, you got to prove closed under multiplication. Remember, this is my scrap sheet of paper, so this is just my thoughts being put down, and then I start afresh and write it in proper paragraph form. Dot your I's, cross your T's, complete sentences, use the appropriate definitions and theorems to do your logical conclusions here. So, I got to show three things: non-empty, closed under subtraction, and then closed under multiplication. To show it's non-empty, alright, start yourself out with what the givens. So this is what you want to show. It's a subring. Now, what are the givens? You're given that phi going from R to S is a homomorphism. Where R and S are rings. I want to show this thing as non-empty. Again, the key is that set notation. Why is this thing non-empty? Well, first off, R is a ring. Being it's a ring, guess what element's inside of R? Then 0R is an element of R because it's a ring. Also, phi of 0R is equal to who? Now this is a theorem you're going to need to know because you're going to quote him quite a bit. That's Theorem 3.10. Phi of 0R is equal to 0s by Theorem 3.10. Zeros always map to zeros. Hence, 0R, that's my guy, is an element of K, and K is non-empty. Now again, underlining, emphasizing the concepts. 0R is an element of R, that's been satisfied. Phi of 0R equals 0s, that's been satisfied. This is where I come from, this is the property I have, I'm done. 0R is inside of K. Now right here is where a lot of people get confused at, and it's the setting up of closed under subtraction, because once you get that down, it pretty much follows for free about closed under multiplication as long as you actually do the appropriate replacing of the subtraction with the times and using the appropriate properties of multiplication. So, to show closure under subtraction, you got to give yourself two guys. So you start with let, pick yourself your favorite guys. I like X and Y. I want to let that be an element of K. Since we've proven in the first part it's non-empty, Well, I get for free that since it's not empty, there's got to be some dudes there. Let's call them x and y. What does that mean? You state immediately, based upon your set notation, what it means to be inside of K. Thus, x and y are elements of R, and it has the property that when I take phi of x, same element here, I'm going to get 0 and s. And phi of y, I'm going to get 0 and s. Now, I want to talk about closure under subtraction. So those are my properties. Now let's talk about subtracting the two elements. Well, you first got to talk about making sure that the subtraction is inside of R. Well, since x and y are in R, then x minus y is an element of R. What's my reasoning there? Well, because R is a ring. And rings have closure. And here comes the other part. What about phi of x minus y? We're going to take phi of it. See, we get this property here. It's the same element, x minus y. It's in R, and phi of x minus y. Well, as phi of x minus y, this guy is going to be equal to, now, here's the gig, phi of x minus phi of y. Now, if it was plus phi of x plus phi of x plus y is equal to phi of x plus phi of y, that's the definition of being a homomorphism. But when it comes to subtraction, that is by Theorem 3.10. Very powerful theorem about the negatives and the subtraction and the zeros. But as you look at this, who was phi of x equal to? That was equal to 0 and s, minus who is phi of y equal to? 0 and s, and that's by substitution. And s, 0 minus 0 is pretty much 0 there. So you got 0. That's going to put x minus y inside of K. Because why? X minus y is an R. Check. Phi of x minus y is equal to 0 and s. Check. X minus y is in K. Now again, you have to go back and write this stuff up. And then, for part 3, I'm going to use the exact same guys, catch the pattern, but I'm going to actually focus on the multiplication. And again, you have to follow the reasonings behind it. What theorem or what definition allows me to do what. So that statement reason that you're going on. The next one is a little more challenging. But as we mentioned before, while we study homomorphisms, they are property preserving. Property preserving. So on this particular problem, what did I give you? So we'll start with the givens and just write them down briefly. The givens are phi is going from R to S is a surjective. Remember, that means onto homomorphism. From R is a ring and S is a ring. We're also given that T is a subring of R. Now I've got to be very specific how I'm going to use that. T is a subring of R. Now, what do we want to show? We want to show that the set W, which is equal to the elements B from S, this is where I come from S, such that B is equal to phi of another dude, C, when they introduce another letter, it's a great time for subscripts, where C is an element of T. So this one has 3 properties you need to focus on to be inside of W. You have to come from S. You have the same guy has to be equal to phi of some dude, where that some dude actually came from T, the subring of R. Now, again, we want to show that this set W is a subring. And who is it going to be a subring of? Well, the elements come from S, so that'll be a subring of S. You've got to keep an eye on it. So what we're really doing here, if you look at this, is W, or so you got phi going from R to S. W is inside of S. T is a subring inside of R. And so W is all the elements of S such that it's equal to phi of some dude that came from T. So subrings are mapping to subrings is what you're actually proving here. Under homomorphisms, it's property preserving. So again, to show a subring, I got to show three things by our favorite theorem, 3.6. Number one, I got to show it's non-empty. And how do you show it's non-empty? We're going to show the zero elements is inside of W. Which zero element would it be? To be inside of W, you come from S. Number two, you got to be closed under subtraction. And then number three, it's got to be closed under multiplication. So again, it's the same three paragraphs of showing you have an actual subring. Now the zeros shouldn't be too bad. So you start yourself out with, the givens here. Okay, and since R and S are rings, guess what elements are going to be in each one of them? Then 0R is an element of R, and 0S is an element of S. Now remember, you got to be specific where you show T is a subring of R. Since T is a subring of R, then subrings have the zero element. 0 and R will also be an element of T. And as phi of 0 and S would be equal to phi of who? Remember, phi maps R to S. So to get 0 and S, 0 and R has to map to them. Remember, zeros always map to zeros. And that's part of your by theorem. I'll abbreviate theorem THM. You're not actually allowed to do that, but I can because this is my scrap sheet of paper. By theorem 3.10. Zeros map to zeros. So, I got a lot going on here, but let's see if not everything in W has been satisfied. We're talking about W being non-empty, so we want the zero element from S to be in there. Well, to be inside of W, you have to come from S. 0 and S is an element of S. That part's been satisfied. That same element, 0 and S, got to be equal to phi of some dude. 0 and S is equal to phi of 0 and R, and where that some dude inside of the phi must have come from T. 0 and R is an element of T. All three things have been satisfied, hence 0 and S, pay attention who you're talking about, 0 and S is an element of W, and W is non-empty. Okay. Now, the closure under subtraction. So you always start the same way. You give yourself a couple elements. Since you just proved it was non-empty, there's got to be some dudes there. Let's talk about X and Y. Let X and Y be an element of W. Immediately after that, you have to show me what it means to be inside of W. Where did you come from? Therefore, W, X and Y, X minus Y, X comma Y, is an element of W. That's where we came from. And it's got a property of that same element, X and Y, has got to be equal to phi of some dude. See, we're talking about C's, who's kind of an afterthought here. So, and this time, great time for subscripts. There exists a C1 and a C2 element of T, which is inside of R, such that X is equal to phi of the C1 guy and y equals phi of C2 guy. So this is actually setting you up for the closed under subtraction and the closed under multiplication. So you let x and y be an element of W. You tell me what that means. To be inside of W, you had to come from S. Therefore, x and y are elements of S. That's a typo there, excuse me. So x and y are elements of W, therefore x and y are elements of S, because that's where I come from. And there exists a C1 and a C2 in T, such that x is equal to phi of C1 and y equals phi of C2. So I got all three properties going on here for my x and y. We want to talk about closed under subtraction. So as x and y are elements of S, then x minus y has got to be an element of S, because S is a subring. S is a ring, actually, a ring. Okay, and so far we got this part of my W, x minus y is an S. Now I want to have the condition x minus y is going to be equal to phi of some dude. So x minus y is going to be equal to phi of C1 minus phi of C2. That is by the substitution. Well, that's equal to, now phi of x minus phi of C1 minus phi of C2 would be equal to phi of C1 minus C2. And what's my reasoning behind that? Now, if it was a plus, it would be the definition of homomorphism. If it was a times, it would be the definition of homomorphism. But when it's a subtraction, it is by Theorem 3.10. And so I've got x minus y equals phi of some dude. So in terms of my conditions to be inside of W, you had to come from S. You have to be equal to phi of some dude. Now let's talk about why that some dude inside the parentheses comes from T. Well, as C1 and C2 are elements of T, then C1 minus C2 is an element of T, because why? T is a subring. Don't just tell me subring. It's a subring of R. Property of subrings, which it means in a ring it is a ring itself, being a subring. So therefore, understand x minus y equals phi of some dude, where that some dude came from T. Hence, x minus y has got to be equal to, be an element of W. And it's closed under subtraction. Now, of course, this is paraphrasing, and I've talked a lot as well as wrote a little bit down, and you need to go back and redo your paragraphs and clean these guys up and the like. And then I got to go and do the idea of as x and y are elements of W, therefore recopy and then do the multiplication, and then you can quote your theorem 3.6. So this is a very simple, important and simple concept, very straightforward, but the trick is you've got to be equal to this guy. Now there's one part that I left off on this thing and why I needed it, and you need to put this into your proof. The part that I left off here, because I was trying to give you the hint of the ideas, is that word surjective. What does the word surjective mean? It's on to. You see, I'm picking arbitrary stuff out of the wonderful world of S. And if I don't have a surjective mapping, I could pick a dude over here in the S ring that nobody maps to. But if I got a surjective map, so now the zeros, you don't have to worry about it because R and S are a ring. 0 is going to be an element of S. But when I come over here and let x and y be an element of W, therefore x, y, element S, and there exists C1 and C2 in T. Why do there exist C1 and C2 in T? It is because phi is surjective. Surjective map means that I can pick anybody over here in the S world, and somebody had to map to them. And in this case, the way it's defined, some guy is going to be inside of T. But it's because phi is surjective that I'm guaranteed that the C1 and C2 are actually going to exist. Because especially when you play over here in the range world, you don't always pick an arbitrary element that maybe nobody mapped to. So when I'm picking arbitrary elements over here in the S world, that surjective really helps to make sure somebody maps to it. So I needed the surjective here, and when you rewrite this thing for the multiplication, it'll be, when you set it up, it'll be the same reason. C1 and C2 are elements of T, such that x equals phi of C1 and y equals phi of C2. It is because phi is surjective. There exists C1 and C2 because phi is surjective, such that we have these equations. So again, this is my helpful hints on these things. I actually don't want to do the problem for you. I probably did more of the problem than I really should have. But these are very important proofs, not just the ones that you're taking notes off of on the videos, but it is also, these guys are real important problems because, again, it's that structure of the course that you've got to get down subrings, because we're in chapter 6. We're going to introduce a new idea called an ideal, which is subrings with some extra properties. So you're going to see this subring quite a bit, especially when I get you back into chapter 6, and that'll be towards the end of the course. So I hope this has been helpful, and good luck on working on your homework.